చేస్తున్నా. అన్‌మ్యూట్ అయిందిలే. ఓకే. అయింది. అవును ఉంది. అది క్లిక్ చేయనా?
లైవ్‌గా అంతా రికార్డ్ చేసుకుంటున్నాను.
Chandra sir, are you there?
Yes, ma'am.
Is my screen visible?
Visible, ma'am.
Audio?
Yes, madam. Visible, ma'am.
Okay. Audio.
Audio also is okay.
Okay. We'll start in 2 minutes. Hello? Good evening, one and all. Shall I start the class? Okay, in the last class, we have seen what are the different types of instructions and the instructions codes, right? In today's session, we'll see how an instruction is executed, what are the different phases involved in an instruction execution, and we'll also see what are the different register transfer languages for register reference, memory reference, as well as IO reference instructions. First, we'll see an instruction cycle. You know that an instruction, a program contains set of instructions. Any program is a set of instruction. Whenever I say instruction cycle, it is related to the execution of instruction. How you are executing a particular instruction, that depends on the instruction cycle. Whatever the instruction may be, it is. One second, I forgot to record. Okay. So every instruction, when you are executing, it has to pass through some phases, or it has to pass to some stages. Let us see what are the phases of an instruction cycle. Mainly, there are 4 stages. Every instruction has to pass through all these 4 stages. First stage is, first you need to fetch the instruction. What is the instruction you are executing? And that instruction you have to fetch from the main memory. That is the first step. Once the instruction is fetched, you need to identify what type of operation you are supposed to execute, or what type of operation you have to implement. Right? That is decode the instruction. And the third step is, now you know what is the instruction to be executed. What is the instruction to be executed? Using fetch operation. Next, using the second cycle, second stage, you know what is to be done. Either it is addition operation, whatever the operation it is, what operation you have to implement, also known. Now, assume that if you are performing, or if you want to perform an addition operation, you require the operand values. You require the operand values. Where the operand values are present? Obviously in the main memory. So third step is, you need to get the address from the memory location. So you need to know the address. If it is a direct address, right? When you see the format of instruction register, 15th bit, IR of 15th is given for what? It decides whether it is a direct address or an indirect address. If it is an indirect address, that means it gives the address of the address. So you need to get the address of the address, which is known as effective address. So we should read the effective address from the memory if it is an indirect address. If it is a direct address, using that address value, you can directly fetch the operand. You can directly get the operand from the main memory to perform a particular operation. Next, once the operand values are retrieved from the main memory, what you can do? You can proceed with your instruction execution. These are the 4 stages involved in any instruction execution. First, we need to fetch the instruction from the memory. First, fetch the instruction. Next, decode the instruction. Decoding the instruction is something like identify what is the operation to be executed. Third step is, to execute that operation, you need to get the effective address from the main memory, because you require the operand values to implement any operation. Once the operand values are fetched using this effective address, you can proceed with your instruction execution. Right? So these 4 steps are to be executed for every instruction in the program. If your program contains some 100 number of instruction, all the hundreds instruction has to go through all these 4 stages. Now, when this instruction cycle will stop, whenever your computer encounters a halt instruction, then only instruction cycle is stopped. Whenever a halt instruction is executed, then you can stop the execution of the instruction. So these are the phases of your instruction cycle: fetch instruction, decode, get the effective address, execution. Clear? Next we'll see each and every stage. What are the register transfer languages involved in every phase of an instruction cycle? First one is fetch and decode. We'll see both fetch and decode here. First we'll see what is a fetch phase. So fetch phase means first you should know what is the instruction to be executed. In which register you can know the address of the next instruction to be executed. In which register you can have the address of the next instruction to be executed. Any answer? You have 8 registers, right? Which register holds the address of the next instruction to be executed? Program counter. Yes, program counter is the one which holds the address of the next instruction. Right? Now, from this program counter, you can know what is the next instruction to be executed. The address of the next instruction. Means in the main memory, in which location, whatever the instruction you want to execute, that can be known. So, first step is, in the first cycle, that is at T0th cycle, what we are doing is, you are moving the address present in the program counter into your address register. Into the address register. That is the first step done at 0th clock cycle. In the next clock cycle, what happened? Now you know what is the instruction to be executed, and where that instruction is present, that is also known, because we have stored the address of that memory location in AR register. So next what we have to do is go to that memory location. M of AR means, assume that if your AR is 100, then M of AR is pointing to 100th location in the main memory. So in this 100th location, your instruction is present. So whatever the instruction is there at 100th location, retrieve that instruction, place it in the instruction register, because IR is the register which holds the instruction to be executed. Right? So go to this memory location specified by AR, fetch the instruction from there, place it in your instruction register. At the same time, you need to increment your program counter. Why? Because program counter always holds the address of the next instruction to be executed, right? So initially PC is equal to 100. Assume that if PC equal to 100, you have fetched the instruction from 100th location. So again PC has to be updated to 100 plus 1. So these are the 2 steps to be done at the first clock cycle. Fetching the instruction from the main memory, at the same time updating the program counter value. Now fetch stage is done. Fetch stage is completed. What is the second phase? Decode the instruction. Now in the last class we have seen the control organization of a basic computer. There I told you what are the 3 bits used for decoding. What are the 3 bits of your instruction register used for decoding? Can anyone tell me which 3 bits are used for decoding? Which 3 bits of your IR are used for decoding? Can anyone tell me? Your IR is the register which is of size 16 bits, and in the 16 bits, opcode bits, that is bits from 12 to 14 bits are used for decoding. Just go through the previous class. There I explained this control organization, control unit of your computer. So here we have seen that this is your instruction register, right? So these 3 bits, these opcode bits, you are providing as an input to 3/8 decoder, which will give you 8 different functions from D0 to D7, right? So decoding is done by using the 3 bits of your instruction register. So at second clock cycle, what we have to do is you need to decode the instruction. That means you need to provide these 3 bits to the 3 by 8 decoder, which will give you 8 different values D0 to D7. 8 values were given. 8 values represents 8 different operation. Right. Now, these are D0 to D7. And in these D0 to D7, what type of instruction this IR is holding? Whatever the instruction we have in IR, what type of instruction it is? Whether it is a memory reference instruction, register reference, or it is an IO instruction, that is to be decided. So how you got this D0 to D7? Because you are decoding the bits of IR register. Which bits you are decoding? 12 to 14 bits of IR register we are decoding, and your IR contains 0 to 11 bits for address field. So 0 to 11 bits of IR are moved to your address register. Why? Because this is your address part, right? I explained when I explained the format of instruction register, there I told you 0 to 11 bits are given for address, 12 to 14 bits are given for opcode, and this 15th bit is ith bit, which represents direct or indirect address. So 0 to 11 bits are stored in the address register, and 15th bit of your instruction register is your ith bit. Now these 0 to 11 bits, if your instruction is a memory reference instruction, then the 0 to 11 bits specifies what? The address. 0 to 11 bits specifies the address. Why? Because here, if it is 0, 0, 0, if the opcode values are 0, 0, 0, then the register, what type of memory reference instruction it can be? 0 triple X, that is AND operation. If it is 0, 0, 1, add operation. If it is 0, 1, 0, 0, 0, 1, it can be LDA operation, STA operation. All these memory reference instruction we have seen in the previous class, right? So if this instruction register is a memory reference instruction, how to tell whether it is memory reference or not? That I will explain. So assume that if your IR contains a memory reference instruction, then these 12 bits, 0 to 11 bits, specifies the address of the operand, specifies the memory location. Next, in the same way, assume that if it is a register reference or an IO reference instruction, register reference or IO instruction, just to see this instruction format for register reference and IO instruction. You know that for register reference instruction, these 4 bits were fixed, right? 0, 111 is fixed, and 0 to 11 bits specifies the type of the register reference instruction. 0 to 11 bits specifies type of the register reference. In the same way, if it is IO instruction, then these 4 bits are fixed. What are those values? 1, 111, and these 11 bits specifies the type of the IO operation. Is it clear? Now, here also, if it is a memory reference address, then this IR contains the address. If it is register reference or IO instruction, then this IR, whatever is there in AR, that specifies the type of the register reference or IO reference instruction. You know what is this ith bit, right? If it is a register reference instruction, what will be the ith bit value? Ith bit, IR of 15 should be equivalent to 15. 0, sorry. In the same way, if it is IO instruction, IR of 15 should be equal to 1. That is what I have included here. If it is register reference, 15th bit of instruction register should be equal to 0. If it is IO instruction, that 15th bit is equivalent to 1. Clear? Now, what we have done here? We have decoded the instruction. In the second cycle, at T2 clock cycle, we have decoded the instruction. Now the instruction has been decoded. Now you need to identify what type of instruction it is. Then only you can proceed with instruction execution. What type of instruction it is? That is always decided by the value of D7. So when you provide these three inputs to 3/8 decoder, it is giving you values from D0 to D7, right? So what type of instruction this IR is holding, that is always decided by value of D7. Using this value, you can decide. If D7 equal to 1, if D7 is equal to 1, it can be either a register reference instruction or an IO instruction. If D7 equal to 1, it is register or IO. How to identify register or IO, that also I'll explain. In all other cases, that means if D7 is not equal to 1, for all the values of D0 to D6, then it represents a memory reference instruction. Okay? Let us see the cycle of instruction cycle. One second. One second. So this is your instruction cycle, right? So what is the first step? Means you haven't started the execution. You haven't started the instruction execution. Then the sequence counter should be equal to 1. As you haven't started the execution. So here sequence counter is equal to 0. So initially your sequence counter is 0. Means clock cycle. Nothing is started. So no clock cycle. Next, what is the first step? First, that is at T0th second, in T0th clock cycle, what we have to do? First, identify what is the instruction to be executed, or where that instruction you want to execute is present in the memory location. Always that address is present in the program counter, right? So first, whatever is there in the program counter, that should be moved to your address register. Instruction, address of the next instruction to be executed is to be placed in address register. Next, what is the next step? At T1 second, what will happen? You know where that instruction is present. So go to that memory location. Go to that memory location and retrieve the instruction. Place it in your instruction register. Place it in instruction register. Now, at the same time, you need to update your program counter or increment your program counter, because if it is 100, you have retrieved that 100th location, instruction present in 100th location. So your PC should be updated to the next value or to the next instruction to be executed. Now this is your fetch phase. What is the second phase? Second phase will start at T2th second. That is your decode stage. How you will decode the instruction? Always decoding is done using opcode bits. That is, using 12 to 14 bits of your IR, you can decode the instruction. Decoding the instruction means what? Just identify what you want to do or what type of operation you have to perform. Next, the 0 to 11 bits specifies the address. So they are to be moved into your address register IR, and 15th bit has to be moved into ith flip-flop because it represents a ith bit, that is direct or indirect bit. Next, once you have decoded the instruction, you need to decide whether it is register reference, memory reference or IO reference. That is always based on the value of D7. If D7 is equal to 1, it can be either a register reference or IO. In other cases, that means if it is not equal to 1, it is memory reference instruction. Now, so either register or IO. How to decide if it is register or IO? So that is based on the ith bit value, because here when you see in for register reference instruction, the ith bit value is 0. For IO instruction, ith bit value is 1. So whenever D7 equal to 1, check the value of the ith bit. If ith bit equal to 1, it represents an IO instruction. If it is 0, it represents a register instruction. Next, what you have to do, you know what type of instruction it is. Next, using the value of 0 to 11 bits, you can know what is to be done or what is to be executed. So the corresponding instruction, the corresponding IO instruction can be executed, and similarly you can execute the corresponding register reference instruction. So your instruction is executed. Once the instruction execution is done, the current instruction execution is done, what you have to do? When you see these phases of this instruction, once this instruction execution is done, this cycle is to be repeated for every instruction in the program. So after this fourth step, the control will go back to the first step. So again, for the next instruction, the same process has to be repeated, right? So here what you have to do, you need to make the sequence counter to 0 for the next instruction, and again you can retrieve the address of the next instruction to be executed from the program counter, place it into AR, and you can follow the same procedure for the remaining instruction. Now here, if it is 0, if the value of D7 is 0, it is memory reference instruction. Only one possibility, memory reference instruction. But memory reference can be either a direct reference or indirect reference. So that always based on the value of your I. If I equal to 0, it represents a direct addressing mode. If I equal to 1, it represents an indirect address. That means address of the address. So you need to get the effective address. You need to get the effective address. So what we have to do? Your AR contains the address of your address. Address of the address. So that address has to be moved into your AR if it is an indirect address. If it is direct, you no need to read the effective address because that is the actual address. You can directly go to that address location and fetch the required operands, and you can proceed with the execution of the instruction. Right? If it is indirect, then only this step is required. After that, you can execute the corresponding memory reference instruction. Once the instruction is done, execution is done, made the sequence counter to 0, go back to step 1. That means fetch, decode, and execution will be continued for all the instructions. Right? Now we will see the register. In the previous class, we have seen what are the register reference instructions we have. Just the name of those register instructions we have seen. Now we will see what are those register reference instructions, memory reference instruction with respect to the corresponding register transfer languages. We will see the corresponding register transfer languages for every instruction we will see in this class with corresponding to your instruction cycle, respect to the instruction cycle. First, let us see register reference instruction. How to know that the instruction is register reference instruction? Obviously, by using the value of D7. If it is 1, then check the ith bit value. If it is 0, then it is a register reference instruction, right? So when D7 equal to 1, there is a possibility that instruction may become a register reference. Next, once it is 1, check the ith bit value. Check the ith bit value. What should be the value? It should be 0. It should be 0. And in which clock cycle you are identifying that it is a register reference instruction? At T3. At T3 you are identifying. So all the register reference instructions were executed at D7. That is 1. I complement, because I should be 0. I equal to 1. Then I complement becomes 0. I complement. And T3 at T3 cycle. If all these three becomes true, then only the instruction will be the register reference instruction, right? Next, you know, it is a register reference instruction, but in register reference also we have different types like complement AC, complement E bit, shift E, AC and E, all that we have different instruction, right? So what type of register reference it is? That is always based on what? That is based on the value of 0 to 11 bits, because it will specify the register operation, corresponding operation. Now see one by one. So these are the instructions executed. These are the different register reference instruction. So these are the operations, and this is the timing cycle or the bit values. This represents the bit values in the instruction register. This represents the register transfer language for a particular operation. This is just the explanation, right? So in this table, what are the bit values set to 1? Which bit values are set to 1 to become a register reference instruction? What type of operation it is, and the corresponding register reference instruction, register transfer language is defined. First we'll see. I think you remember this format, right? So for register reference instruction, these bits are fixed. Opcode bit value should be equal to 3 and the ith bit value should be equal to 0 for register reference instruction, right? Next, by changing these 12 bits, by changing the value in these 12 bits, then different instructions will come. If it is 1, so which bit it is? This is your 11th bit. If you set the 11th bit of IR to 1, then which instruction is executed? CLA instruction is executed. So R is common for all. What is R? R means D7 I complement T3. This R is common for all the register reference instruction. So R D11, because we are setting this 11th bit as 1. We are making this 11th bit as 1. Then CLA instruction is executed. What is the CLA? Clear the accumulator. Clear the accumulator. So how you will write the register transfer language? AC tends to 0. Clear the content of your accumulator. Next, what you will do? Made this 11th bit as 0, and if you made this 10th bit to 1, another instruction will be executed. Like this, we will change all the bits so that you will get different register reference instruction, right? We have seen this in the previous class. So if the 10th bit value is equal to 1, then CLA instruction is executed. What is CLA instruction? Clear E. You know what is E? E is extra bit. When you perform addition or subtraction operations, carries and borrows are generated. They will be stored in your extra bit. So made that extra bit, made that content to 0. That is clear E. Next, if your 9th bit value is 1, what is executed? CMA instruction is executed. Complement AC. Complement AC. Complement means made 1 to 0, 0 to 1. 1 is converted to 0, 0 is converted to 1. Complement AC. AC becomes the corresponding register transfer language is AC becomes AC complement. Next, if the 8th bit value equal to 1, then CME complement E. E complement. Now see these two. If the 7th bit value is 1, the instruction executed is CIR. Circular right shift AC and E. Perform circular right shift on AC and E. Now, when you perform the circular right shift, this is the corresponding register transfer language. That is AC, what you are doing? Apply a right shift on AC. Apply a right shift on AC. And when you remember this right shift operation, shifting operation, whenever I perform left shift, what will happen? When you perform the left shift, your MSB bit is discarded. A serial input of 0 is transferred to the LSB position. Similarly, when you perform a right shift operation, what will happen? A serial input of 0 is transferred at MSB position and LSB is discarded, right? So here what we are doing? Circular shift on AC and E we are performing. So just on AC, perform a shift to right operation, and when you perform shift to right operation, the content will be like this. So let's assume that this is your accumulator containing the bits like this. When you perform a right shift operation, what will happen? Generally, this bit is a serial input of 0 is transferred here. If it is a logical shift. If it is a circular shift, what will happen? This MSB position will be moved to, this LSB position will be moved to the MSB position. But here, what we are doing is, you are applying a circular right shift on AC and E. So, this 15th bit of your accumulator is filled with the data present in E. 15th bit is filled with E. Similarly, here, if it is a normal operation, normal logical shift right operation, you will simply discard this LSB position, right? But it is circular one. So circular means what? Data should not be lost. So when you place this E content into AC, E content is not lost. In the same way, AC content, the data present at 0th location of your AC, you are moving it into your E. That is what I have written here. So whatever is present at 0th location, that you are moving into E. Whatever is there in E, that you are moving into 15th bit of accumulator. If it is a CIR operation, what happens at CIR? Make the 7th bit of instruction register to 1. Next instruction is RB6. Make the 6th bit of the instruction register to 1. What is to be executed? CIL. CIL means circular left shift AC and E. Circular left shift AC and E. How it will be done? Apply a shift to left on AC. Just see the example. This is my AC. When you perform a left shift operation, the bits will be moved like this. If it is a normal logical shift, what happened? You will simply discard this MSB bit and a serial input of 0 is transferred to the LSB position. But here, you are applying a circular shift left on EC and E. So what happens is, this bit is not discarded. So place this bit, 15th bit is copied into E, and whatever is there in E, that you place it into the 0th bit of accumulator. That is what we have written here. So whatever there in E, place it into 0th bit. E is copied into 0th bit. And 15th bit, whatever is there in the 15th bit of AC, copy that value into E. Next, if the B5 equal to 1, if the 5th bit of your IR is equal to 1, INC operation is performed. INC means increment. What is to be increment? Increment the content of the accumulator. AC equal to AC plus 1. Second, next is RB4. If B4 equal to 1, then SPA. Skip the next instruction if the value is positive. Which value? If the accumulator is positive, skip the next instruction. Now the question, how to know whether the whether the value is positive or negative. In the previous classes, I explained how to know whether the value is positive or not negative based on the MSB bit. If the MSB bit is 0, it represents a positive value. If the MSB bit is 1, it represents a negative value. SPA means skip the next instruction if it is positive. If 15th MSB bit means what? As the size of accumulator is 16 bits, so MSB bit represents AC of 15. If the 15th bit of accumulator is 0, it represents a positive value. So if it is positive, skip the next instruction to be executed. Where the address of the next instruction to be executed is present, it is present in PC. So you need to skip that value. So update the PC value. Assume that if PC contains 100, generally you have to execute the 100th, the instruction present at 100th location. Next, in the sequence, you have to execute that. But here, that instruction is to be skipped. So, make PC to PC plus 1, the next instruction. Similarly, if B3 equal to 1, SNA is the operation. SNA means skip the next instruction if it is negative. Skip the next instruction if it is negative. So if it is 0, if the MSB bit is 0, it represents a positive. If the MSB bit of accumulator is 1, it represents a negative value. Then skip the next instruction, made PC equal to PC plus 1. And then if B2 equal to 1, what you have to do? SZA. Skip the next instruction if the accumulator value is 0. If AC equal to 0, then skip the next instruction. So update PC to PC plus 1. Similarly, RB1. If B1 equal to 1, skip the next instruction if E equal to 0. That is, if extra flip-flop value is 0, skip the next instruction. So, E equal to 0, PC equal to PC plus 1. And the last one is, if 0th bit of IR is 0, then HLT operation is executed. Halt the computer. So, then what you have to do is, made the S flip-flop. S flip-flop is set whenever you start the computer. So, whenever you start your computer, it is made to 1. You will start this start flip-flop. So you are halting your computer. So made the S value, S flip-flop value to 0. Then your computer will halt. Okay? So these are the different register reference instructions and their corresponding register transfer languages. Any doubts? Did everyone understand? Shall I move on to the next topic? Okay. Next is memory reference instructions. I'll tell you 2 or 3 instructions, ma. So memory reference instruction. You know when a memory reference instruction is executed. If D7 equal to 1, then it is either register reference or IO instruction. For all the values of D0 to D6, a memory reference instruction is executed, right? So you know what are the memory reference instructions you have. They are AND, add, LDA, STA, bunch unconditionally, BSA and ISZ. So you know that these are the 7 instructions, 7 memory instructions. Now we will see in which clock cycle they were executed, a corresponding operation is executed. What is the respective register transfer language? We will see now. First instruction is AND instruction. AND means what? you need to perform AND operation with the data present in the accumulator and with the data present in the memory. So first, whenever the values of D0 equal to 1. So here we got D0 to D7. 8 values you got. In these 8 values, if D7 equal to 1, it represents a register or IO instruction. For all these values of D0 to D6, memory reference instruction is executed. For all the values, if D0 equal to 1, it can be a memory. If D1 equal to 1, then D2 equal to 1, D3, D4, D5, D6. For all these values, memory reference instruction is executed, right? And in which clock cycle memory reference instruction is executed? In which clock cycle memory reference instruction is executed? T4. In T4, memory reference instruction is executed. See here. So at T3, what we are doing, in case of memory reference instruction, at T3, you are fetching the effective address if it is an indirect. If it is direct, you are performing nothing. Nothing is performed. In the next clock cycle only, you are executing the memory reference instruction. If it is a register reference or IO instruction, in T3 clock cycle, you are executing the corresponding instruction, right? But for memory reference instruction, the execution starts from T4. Execution starts from T4. So first, when you see the format of this instruction register for a memory reference instruction, so this is your ith bit. It can be either 0 or 1. So these opcode values, 12 to 14 bits of your instruction register specifies what? The type of the memory reference instruction. The type of the memory reference instruction. If it is 001, if the opcode value is 001, sorry, 000, then it is 0. The corresponding value is 0. If it is 001, then the corresponding value is D1. The value is 1. So D1th line from this decoder is selected, chosen. So if these opcode values are 000, then D0 is selected. If it is 001, D1 is selected. 010, D2, 011, D3, 100, D4, 101, D5, 110, D6. Clear? So based on these values of the opcode, a particular memory reference instruction is executed. Right? So with what instruction is given for which decoded line, which line of this decoder? So for if it is a D0, if it is D0, then AND operation is executed. When you choose D0, AND operation is executed. Right? So you know how to perform AND operation. First, to perform AND operation, you require two values. One value is present in the accumulator. One is present in the accumulator. Second data is go to the memory location. Here 0 to 11 bits specifies the address, right? From which memory location you need to retrieve the required data, that will be specified in this address field, right? So if this address field is something like 50, so if your AR equal to 50, you know that 0 to 11 bits of IR are placed in the AR. When you see the instruction cycle, just to see this instruction cycle, ma. So 0 to 11 bits of IR you are placing in AR. Now, so first go to that memory location AR. That means if it is 50, go to 50th location. Whatever the data is present at 50th location, that is to be moved into your data register, because data register always holds the data retrieved from the main memory. So go to M of AR and place it in DR. That will be done at T4th clock cycle. But there the AND operation is not ended. Next, so here you have retrieved the data from the main memory and you already have the data present in the accumulator. Now you can perform the AND operation in the next clock cycle. That is at T5, you can perform AND operation on AC, and where you have placed the data, you have placed the data retrieved from the main memory into DR. So perform an AND operation on AC and DR. Now the instruction is done. Instruction is completed. Whenever an instruction is completed, what you are doing? Made the sequence counter to 0 and go back to the first step. So made the sequence counter to 0. This is your AND operation. Clear? Similarly, second one, with this I'll stop. So second one is what? Add operation. For ANDing or adding, you require the two data content. So you know what is the first content. So first value is present in the accumulator. One data content is present in the accumulator. What is to be performed? Perform the addition operation on data present in accumulator with the data present in the memory location. Right? So these 0 to 11 bits are moved into your AR. So go to that memory location. Whatever is present in that memory location, retrieve that data, place it in DR. Place it into DR. And when this add operation is executed, whenever D1 equal to 1, if D0 equal to 1, that is, if the opcode values are 0, 0, 0, then the corresponding decimal value is 0. Whatever is connected to the 0th line of decoder, D0, so that will be chosen. Now, if the opcode values are 0, 0, 1, the corresponding decimal value is 1. So the line connected to the first, the one which is connected to the first line of decoder is D1. So for D1, add operation is executed at T4th clock cycle. So place the content of the memory into data register. Now in the next clock cycle, you can apply addition operation on AC and DR. Place the result back into accumulator. Now, whenever you are performing the addition operation, or there may be a chance to get the carry values. Cout is a carry value where you have to place the carry values or the borrow values. E extra flip-flop is used for placing the carry values and the borrow value. So, whenever this addition is performed, if a carry is generated, place that carry into E flip-flop, that is extra flip-flop. Now the instruction execution is done, so you can make the sequence counter to 0. Clear? And the third one is, shall I continue? Let me know, ma. Shall I continue with the next memory reference instruction? Today I am not going to conduct the quiz, ma. You just go through these slides. Tomorrow I'll conduct. Because in the beginning we got the instructions that we need to end up the class by 4:50 itself. That is the reason we didn't put any quiz. Tomorrow day after tomorrow you'll have quiz. So what you will do is, in these 2 days, you please go through these slides. I'll share whatever I have discussed today. You please go through them, and you also refer the previous class. Once the previous class is understand, then only you can understand what I have taught in today's class. So go through the PPTs. If you have any doubts, you can ask them. You can send a message in the WhatsApp group, or you can send a personal message to me. I'll clarify your doubts. Okay. Did everyone understand today's class? If you have any doubts, you can post it in the chat box. Did everyone understand? If you don't refer, you will get confused in the next class, ma. That is the reason you must read whatever I taught today, and it should be compared with the previous class. Then only you will understand. You keep that control unit at one side, and the format of register reference, memory reference, IO instruction. You should have the control unit and all these formats in a page and go through each and every instruction one by one. First go through register reference instruction, and tomorrow I'll complete these memory reference instruction as well as IO instructions. With that, I think your first unit will be completed. After that, I'll try to revise the topic. So what you have to do is, you please go through the first unit. Mostly by Thursday, I'll finish off the first unit. So if you have any doubts, you please let me know the topics. You will, once you read the complete unit, then only you will get the doubts. So go through the complete first unit. Let me know the topics which you did not understand. Someone is asking me to explain the complete unit, but revising the complete unit is difficult. So let me know what are the topics you did not understand, so that I'll try to revise them in Saturday's class as well as in the next Tuesday's class. After that, your unit test will start. 1 to 1 to 12 and 12 12. You are asking me to send the PPTs. Okay, I'll send. After this session, we'll send the PPTs. Every day we are sending, no? We'll send the PPTs. Okay. Still any doubts? Okay. Shall I close the session? Okay, thank you. We'll send the recording also. We'll share it in a Google Drive. The recording will be shared in a Google Drive. Thank you, ma. I am ending my session.